continuing on with the limit discussion that we had yesterday. This is the first of the three main topics. I said that the other day also. This is the shortest one, and in my opinion, probably the easiest one. It's not easy, but it's the easiest of the three. So, what are we talking about? First, we're going to start with this. Figure out what a limit is. We talked a little bit, or I talked a little bit about that the other day. We're going to look at a numerical and a graphical approach. What does that mean? That means we're going to try to find the numerical value, the number. How are we going to do that? A couple different ways. One of the approaches will be to just simply look at a graph. There are certain instances when you can't find the limit. We talked a little bit about that yesterday. Then we're going to talk about all the different techniques that you can use to find that numerical value. It is very common to see a limit problem where you don't have a picture and you've got to figure out a way to find it algebraically. And then we're going to get to something towards the end called the Squeeze Theorem, which is a little nasty, but I'll try to go slow. Okay? And then you should be able to fit at least 20 grapes in your mouth without choking. Anybody ever test it? No?
Have you?
Oh, yeah. 20, easy. I think I did like 32.
Okay.
I don't
Is
know
there
if
a
I
world record?
How? No. No, I'm not part of the Guinness Book of World Records.
No, I was just saying, is there?
Oh, I don't know. I've never looked. You know who would know? Google. Okay, so notation. What is the limit as x approaches 4 for the function x squared? Just as an example here. We talked about that Monday. Then we had two subsets of that. What happens when we come from the right-hand side or the positive side, and what happens when we come from the left-hand side or the negative side. And they're handled very differently as we looked at on Monday, and we'll delve a little bit deeper into that as we progress through the selection. Remember that the answer to a limit problem is a numerical value. What is the y value that you're getting very close to as the x value gets very close to that number below the limb? So what is a limit? We talked about this example also. So I've got some function, we don't care what it is. I'll tell you what it is in a second. And all of a sudden I got a hole in it. So what happens when I approach that hole? So first algebraic example is that. Ooh, yeah, I heard out of that one. Nobody likes the rational function involving two quadratics stacked on top of each other. First thing, you must get burned into your brain. Anytime you have a limit problem, the first thing you do is plug and chug. Okay, so do that. Plug and chug. In other words, get out your calculators, put 4 into that function, and tell me what you get. Are you taking paper on notes?
Yeah, I just want Thank you.
I meant to ask, every time I exit turns to 2 and every time I like...
Your mind? Yeah.
So that's your mode button.
It's used with everything.
Perfect.
Oh, thank you.
I just never ended up getting one.
Okay, what happens? 0 over 0. What do we already know about 0 over 0? Undefined. Icky bad. Not good. Okay? It doesn't matter. If you plug and chug and you get a numerical value, you're done. Okay? So for instance, suppose I change that 4 to a 5. Plug and chug. Do it again, but with 5. Tell me what you get for an answer.
0.7125.
Watch out for that. All right, I'll trust you on that one. 0.7125. Oh, by the way, AP standard, 3 decimal places. Always. 0.713. Can somebody confirm that, by the way? Are we going to trust Adrian?
That's not what I got.
Oh, boy.
That's not what I got either. I got 0.85 also.
0.85?
Yeah. Well, it's 17 over 12.
He's in radians mode.
Shouldn't, yeah, that's funny. Shouldn't matter. Point, say it again. 0.8.
8.5.
0.85. Okay, that's easy, and that's the ideal system. What does that mean? If you look at the graph, if I come up to, this isn't the graph of the function, but if I come up to the graph, it's literally the value of the function at that point. Okay? So that's great. Those are the easiest limit problems to do. You plug and chug, you're done. But what happens when we do something like this, where we get 0 over 0? Okay. Step 2, algebraically manipulate. What can I do to that function to make my life easier? Go.
To factor it?
Good. Factor that, please.
Put algebra review there.
We won't get this error fixed soon. We're going to find a new classroom. Okay, what happens when you factor? Does anything cancel? Are we on the struggle bus here? Or?
No, just
Still working? Okay, that's fine. No problem.
In both the top and the bottom, x minus 4 is a vector.
Okay, so let's go from scratch just to make sure we got everybody with us. Matthew, what's the top? How's it factor?
4x plus 7 in parentheses times x minus 4.
And the bottom?
X minus 4 in parentheses times 3x plus 5.
Say again.
Times 3x plus 5.
I think it's 2x and 7.
Yeah.
2x to 7.
Uh-oh.
That one's really good.
I was just about to ask.
Yeah.
Okay, so now we're all good. Okay, so back in Algebra 2 or Pre-Calc, we learned that this cancels. And that is what generates that hole. So back in Algebra 2 or Pre-Calc, we would say no value at the function there. That's why there's a hole there. Calculus is a different story. Remember, the limit is the y value that we get very close to as we get very close to 4. We don't care about 4, we care about getting close to 4. Since we were able to algebraically manipulate that, we can then plug and chug again. Okay. So when you do that, we get a nice pretty answer of 15/17. Plug and chug first. Oops, there's a problem. Try to algebraically manipulate. Plug and chug again, you got your answer. That's not always going to work, but for the most part, that will get you through a good chunk of these limit problems. Because there's got to be a value at the function. I said that wrong. There's got to be a point, a y value that you're getting close to on the function. So this is the basic concept of limits. Before I go any further, does this make sense? It's fairly foreign to all of us because we want to know, we've been programmed to ask the question, what's the value of the function? And now we're changing that mindset and saying, I don't care what the value of the function is, I care about what the value is becoming as you get very close to it. Okay? Beautiful. There's our notation. General notation, calculus speak if you will. The limit of some function as x approaches a, where a is a constant, is going to equal capital L, which stands for the y value of the function. The limit value. Just a different way of showing that. I've got some function. As this value of x gets closer and closer to a, the value of the function gets closer and closer to L, whether you come from the left or the right-hand side. We'll address the whole left and right-hand side in a minute. Okay. What about this guy? Hopefully, you know what that function looks like, do you? If not, bust out your calculator and graph it. That is one of our mother functions. It looks like that. Save the hassles. We hinted at this a little bit yesterday. What happens when I approach 0 for that function? What's the y value? What did you say? Why?
Because they're both going opposite ways.
They're both going opposite ways, so it doesn't work. If they're both going up, that's a different story. If they're going opposite ways, it doesn't work. So we've got the colored rectangle, which is always an indicator that it's probably fairly important. And notice what the notation says. The limit is going to equal that L if the limit from the left-hand side matches the limit from the right-hand side. So in plain English, we get that. The left-hand limit must match the right-hand limit. Okay, so I'm going to back up a little bit. Go back here. Okay. If I come from the left-hand side, I'm approaching the value. If I come from the right-hand side, I'm approaching the same value. Therefore, we're good to go. You thought your office was hot. Step in here. Oh, it feels ripe in here. Hey, everybody, Mr. Levinson.
What's up, everyone? What I love about this, all your masks are up. Looking to learn. Here's the man for you. Enjoy it. It's brutal in here. It's not good.
No, it's not healthy. I should just stop. Nap time?
Yes.
Okay. See ya. All right, so where were we? This guy. Okay. What I didn't address is what happens when we plug and chug. Again, first thing you do, plug and chug, but I think it's fairly obvious. You get 1 over 0. That's bad. You got to find a different way to do it, so we get that. It is conceivable that after you plug and chug, after you algebraically manipulate, after you plug and chug again, it still doesn't work. It doesn't matter what I do to this function, I can't have it approach a value at 0. Okay? That's what causes a limit to fail. This is the function, the absolute value of x over x. It is one of our new mother functions. You've probably never seen that before. Write it down. Can't have a value at 0. Any other number you plug into x is going to give you the same thing over and over again. If you plug in a positive value, you get a positive over positive, which makes it positive 1. If you plug in a negative value, you get a positive over a negative, which makes it negative 1. What's the limit, before we talk about the limit that's listed there, what's the limit if I change this to a 2? What's the limit as x approaches 2? Don't overthink this. 1, thank you. Why? Absolute value of 2 is 2. 2 over 2 is 1. Done. Or look at the graph. Over here at 2, the value of the function is 1, and we're good to go. The more exciting thing is what happens when you approach 0. So this is an illustration of the same thing we saw in the last slide. Coming from the left-hand side, we get a certain value. Coming from the right-hand side, we get a different value. So if we're talking fancy smanchy calculus talk, we would have something like the limit as x approaches 0 from the positive of the absolute value of x, and the limit as x approaches 0 from the negative of the absolute value of x over x. What's this one equal? One. What's this one equal? Negative 1. Left-hand limit doesn't match right-hand limit, so what is the ultimate answer there? The ultimate answer is does not exist. Now the problem, one of the problems is, as soon as you introduce does not exist, people go to that as your go-to for any problem. Problem gets a little difficult, does not exist. Never seen that function before, does not exist. The only way that works is when the left-hand limit doesn't match the right. Okay? Good? We're going to take a break. Then, when we come back from the break, we're going to play a little game. And the game is this. You have to answer a simple question. How many 5-year-olds could you fight? There are the rules.
How much time do I have?
Unlimited time. You keep going until you get taken out. So the question is, how many 5-year-olds can you take out before they take you out? Anybody not understand the question? Good. 5 minutes, go. Leave this sweatbox and go take a break for a little bit. Okay, so this will allow us now to talk about different ways to solve limits. There's a bunch of stuff in here that I'm going to cover that you're going to do without even thinking about it, but you still need to see the calculus speak of how this works. What I mean by that is, here's some examples. Okay, these are just some theorems that apply to limits. Okay, number 1, the limit of b, where b is some number as x approaches c, is just going to be b. Understanding that is not nearly as important as being able to analyze that. So for instance, notice that the function b, where b is a number, is just going to be a horizontal line. Right? So let's say b is 3. It's a horizontal line through y equals 3. Therefore, it doesn't matter what point you choose along the line, you're always going to have the y value of 3. What does the graph of y equal x look like? No. Y equals x.
It's the line with the slope of 1. I guess it's just straight
Yeah, it's that 45-degree angle line that passes through the origin. The thing about being on the line y equals x is that the x value and the y value are always the same. 2, 2, -7, -7. 1500, 1500 is always on that line. Therefore, if you take that line and you plug in some number, you're going to get the same number as a limit. And then if we do something crazy like raise it to an exponent, we're still going to get the same thing. Okay, so it just spits out those values. Those are all examples of plug and chug. Now notice, however, in one, plug and chug kind of breaks down, but then it also doesn't break down. If I'm looking for the limit as x approaches 2 of 3, like it says, there's nowhere to plug in for x, it's just going to spit out 3. Number 2 is the epitome of plug and chug, as is number 3. Then we get this whole big mess. And that's simply what it is it's just a mess. The limit of a sum is the sum of the limits. Find the limit of one, find the limit of the other, add them up, you're good to go. The limit of a product is the product of the limits. Find the limit of one, find the limit of the other, multiply them together. Last year you've seen similar stuff like this with logs. Okay? Logs had a little bit of things in there to screw it up for you. This is about as straightforward as it gets. Now, we're going to apply that kind of stuff to a problem like this. What's the limit as x approaches 2 of 4x squared plus 3? Don't write this down. If you're on the slideshow, fine. If you're taking notes, don't write this down because you're going to see what happens at the end. What I'm going to do is solve this using the properties on the previous slide. So the limit of a sum is the sum of the limits. If I multiply a limit by a scalar or some number, I can move that number out in front. The exponent one we had on the previous slide. And we get down to an answer of 19. Now that's all ridiculous. The reason it's ridiculous is because that's not how you're going to solve the problem. All you're going to do is plug and chug. Okay. So those properties take care of themselves within the concept of plugging and chugging. So why did I give them to you? Because I still think it's important that you see them so that you understand how this works. It's not magic, it's based on some theorems. But you don't need to really understand the theorems because it takes care of itself. Okay, so, got this guy. Not fun. What do we do first? Plug and chug, go ahead. What do you get? 0 over 0. You knew it was going to, it's going to work out that way every time, right? Okay, so 0 over 0. Then what do we do? So remember, step 1, plug and chug. Did it, got a problem. Step number 2, factor. Algebraically manipulate. Does anybody remember how to factor a cubic? Didn't think. Oh, you think so, huh?
I remember that the acronym was SOAP, but I don't remember how to apply it. I just did that for
Stay
same
there.
opposite, always positive.
I've never heard that before.
Okay.
I just know the rules.
Yeah, Gracie came into my room, talked about it, and then left. He
Yeah,
wasn't my teacher.
that guy's operating on a different level.
Yeah.
Yeah, okay. So I'll give it to you. Now remember, with perfect squares, there's only the difference of perfect squares. There's no sum of perfect squares. Cubes are a little bit different. There is one for the sum of cubes. In the numerator, what's A? X. What's B? 1. Good. That's the hard part. Now we just go crazy. When you're solving a limit problem, I know it's a pain in the butt, but you have to write this limit as x approaches whatever every single time until you get an answer, then you're done writing it. So this would become x minus 1 times x squared plus x plus 1 over x minus 1. Oh, and sure enough, that makes me happy because I can cancel. That's a plus, not a 4, by the way. Equals 3. Done. Are there other ways to solve that? Yeah, you could have busted out a calculator, graphed it, looked at that. You could bust out your calculator, put it into y equals and look at a chart, the table. You could graph it on Desmos. If you don't have that on your iPad, by the way, I would suggest you get it from the self-service. It's great. It's basically a graphing program that we'll use quite a bit. Problems. So again, plug and chug. Doesn't work, algebraically manipulate. Plug and chug again. Hopefully you get an answer. If you don't, then something wonky's going on, and it's either going to be DNE or you got to come up with something else. It's that come up with something else that's going to cause the most problems for people. We'll cross that bridge when we get to it. For those of you that know me or have had me for class, I'm not a fan of memorizing. However, there are certain theorems that we're going to run into that we use a lot, and understanding where they come from is not worth our time. Here are two things. What does flashcard worthy mean? I have found people have a lot of success when they start early and start making some form of a flashcard to remember important theorems in calculus. It's a lot easier to do as you go along than when March rolls around or April rolls around and we start reviewing and you try to generate some flashcards. If you choose to do that, there are a couple options. Some people literally will go and get flashcards on, the 3x5 note cards and start putting stuff on there. Other people find a flashcard app. There are a ton of them out there. In fact, there might be some in self-service. But these are our first two theorems that are flashcard worthy. Something, unfortunately, you just have to memorize. And then we talk about how to apply them. So, I have a function like this. So I'm going to go through the whole process again. First thing I do is plug and chug. Tangent of 0 is 0, 0 on the bottom, that's bad, 0 over 0. Can I algebraically manipulate? Yes, I can. How would I algebraically manipulate that? I would turn tangent into sine over cosine. Now this is a big jump for some of you to go from here to here. Let me show you how I did that. The limit as x approaches 0 of sine of x over cosine of x over x. Dividing by x is the same thing as multiplying by 1 over x. So I left the x on the bottom, and this becomes the limit as x approaches 0 of 1 over x times the sine of x over the cosine of x. And then I chose to pair the x up with the sine. One of the things I did on one of the earlier slides is I said the limit of a product is the product of the limit. I know from this slide that the limit as x approaches 0 of the sine of x is 1. I know that the limit as 1 over cosine approaches 0 will also be 1. How do I know it's 1? Because it's a plug and chug. Cosine of 0 is 1. Therefore, I get 1. Questions? Make sense? Probably not at this point. It will as you practice a little bit. Okay. This one's going to get a little ugly. I'll go through it slow. It's not a very common theorem, but it's the reason I'm covering it is for, a couple main reasons. Number one, it's in our syllabus. By that I mean it's something that the College Board includes on the test. Number two, it's a good example of a limit type problem. And number three, what's more important is you understand the concepts. In fact, what I would recommend is just put your pencil down for a while or your stylus for a while and just be mathematical sponges and absorb information. Okay? Squeeze theorem, sandwich theorem, pinching theorem, they're all the same thing. What does it mean? It takes a scenario like this. So notice in that picture, there are three functions, g, f, and h. And so what we establish first is this stuff on top. And that is, no matter what happens, f has to be between g and h. I like calling this the sandwich theorem. Why do I call it the sandwich theorem? Because it makes sense to look at this like a sandwich. So imagine g being a piece of bread, imagine h being a piece of bread, and f being some type of lunch meat. Molly, what's your favorite lunch meat? You eat lunch meat?
I do.
What? Turkey?
Yeah.
Great. So f is going to be a slice of turkey. Bread dealer?
Oh, I don't think that.
Wheat bread. G and H are slices of wheat bread. So Molly's going to make her turkey sandwich, and then she's going to mash it down. No matter how much she mashes that sandwich down, is the turkey going to go flying out of the sandwich? No, it stays between the two pieces of bread. That's the key to this theorem. Okay, so she's got this nice fluffy piece of bread sitting here, and her piece of turkey in there. I don't know what the red stuff is, just, I don't want to think about it. But as she squeezes the sandwich, the piece of bread on top stays on the top, the piece of bread on the bottom stays on the bottom, and the turkey stays in between. Okay. No matter what value h approaches, if g approaches the same value, then f has to approach the same value. So before I go on, does that make sense? Yes or no?
Yeah.
Good? We're good? Okay, that's what's really important out of this, is that you understand the concept. The example that I'm going to show you is nasty. But that's okay. That's not what I really care about. It's that you understand the idea of the sandwich slash pinch slash squeeze theorem. This business that I circled in red has to be true first. If she makes a piece of, or if she makes a sandwich with the turkey up on top of the two pieces of bread, number one, that's just plain weird. And number two, it's not going to apply to this theorem. Whoops, whoa, 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 itchy trigger finger there. Hold on, what just happened? Wow. Get caught up, there, okay, that's, yeah. Okay. That's what we just said. There's the fancy calculus speak nobody cares about. So here's an example. The stuff in the middle, the squiggly thing, is what's called an oscillating function. It bounces back and forth. You've seen that with things like the sine function, the cosine function. This is actually a dampened oscillating function, which means it gets smaller as you get closer to a value. If I zoom in on that, it's never going to hit the answer. It's going to just keep looking like that no matter how far I zoom into it. So I want to know the limit of what happens when that approaches zero. By the way, that function is that. So again, just try to follow me with this and see if it makes sense. First thing I do is plug and chug. Can't. Got a problem. 1 over 0. Not good. I don't know how to algebraically manipulate that. And in fact, I can't. So I'm going to take a different approach. The different approach is applying the squeeze slash sandwich slash pinching theorem. You'll see in that picture I've got two pieces of bread already installed. And I'm going to use that to find the answer. Okay? So this is very confusing, and I wouldn't expect you to do this from scratch, but I did want to show you an example of how this applies. I noticed that in the original function that I've got a sine function in there. And so I said, if I take the sine of anything, t, it's always got to be between 1 and negative 1. Doesn't matter. If t is x, if t is x squared minus 471, whatever it is, it's got to be between 1 and negative 1. So instead of t, I chose to use 1 over x squared. Why 1 over x squared? Because that's what my function is in the original problem. And then I got done building my sandwich by saying, okay, I have to multiply everything by x squared, which I did. So this center thing matches the function. Okay, so I built my sandwich based on those functions. After building it, what I notice is I have functions for my two pieces of bread. One piece of bread is x squared, one piece is negative x squared. And my function, which is the turkey, is always going to be between those two pieces of bread. Doing a problem like this is the hard part, because now I don't care about that at all. Because I know the turkey is going to stay between the pieces of bread, so now I just need to look at the pieces of bread. What's the limit as x approaches 0 for x squared? 0. What's the limit as x approaches 0 for negative x squared? 0. Since I smashed the bread down and they both approach 0, it guarantees that the turkey has to also approach 0. Let me get that. Okay? We're going to get into some scenarios like this where being able to apply the theorem is not nearly as important as being able to understand and talk about the theorem. Can you relate the squeeze theorem, sandwich theorem, pinching theorem to our bread analogy? Or can you explain how that problem works? That's the important part here. Not being able to go from scratch. This is pretty difficult stuff to do. And so the argument is, well, why did you even show us then? Why do we care? Because again, my job is to get you exposed to as much calculus as possible and help you talk about it whenever asked. On the AP test, are you going to get a problem like that where you're going to have to use the sandwich theorem from start to finish? Probably not. But they might ask you a general theory question about the sandwich theorem, like for instance, they would guide you and tell you what the pieces of bread are and see if you can use that in the sandwich theorem to find the value of the limit. Okay? Kind of makes sense? A little bit? Okay, you'll have some time to process it. Whoa, boy. It's all right. I actually don't have, here we go.
It'll evaporate on itself.
Okay, we got some enough. It's probably already dried. All right, so review. Plug and chug. Algebraically manipulate. Plug and chug again at the end. If that doesn't work, look at the graph, guess, or pray. I forgot number 5.5 would be cheat off your neighbor. So, on Friday,